Studies. So, I request Dr. Vivek Parker to introduce the speaker.
Okay. I think Abhijit can start live streaming. Abhijit? Yeah, okay. Good evening. It is my pleasure to introduce Professor Antonio Moro. He is Associate Professor at the Department of Atomic, Molecular and Nuclear Physics of the University of Sevilla in Spain. He works in theoretical nuclear physics with emphasis in the description of the structure and reactions of weakly bound and exotic nuclei. He obtained his PhD at the University of Sevilla in the year 2001. Then he moved to the Technical University of Lisbon, where he worked as a postdoctoral fellow. In 2004, he returned to the University of Sevilla with a research contract, and in 2010, he became associate professor at the university. Much of his research work has been performed in close collaboration with experimental groups participating actively in the interpretation of nuclear reaction data measured at several radioactive ion beam facilities, such as Isolde in CERN, Ganil, France, Ribras in Brazil, Notre Dame in USA, and RIBF RIKEN in Japan. Personally, I know him as a fresco expert. He has worked closely with Professor Ian Thompson for the development of the well-known versatile code Fresco. He was also responsible for development of graphical interface for Fresco named Xfresco. Many of us have contacted him several times for any doubts regarding Fresco calculations. He has always promptly replied to our queries and helped us in the calculations. When I was a postdoc with Professor Ismail Martel at University of Hulwa, which is around 50 kilometers from Sevilla, we met several times for collaboration meetings as well as conferences. Actually, we all wanted to have Professor Moro in our DAE symposium. I have requested him every year, but because of his busy teaching schedule, he could not make it. So by this virtual way, he has agreed to give a talk on his recent work on IAV model, which resulted in two back-to-back physical review letters publications. With this short intro, now I invite Professor Antonio Moro to deliver his talk.
Okay.
Professor Moro. Yeah.
Okay, thank you, Vivek. Thank you very much for the nice and kind introduction. Well, first of all, I should also apologize for the delay in the seminar because you kindly invited me some time ago, and we have been postponing and deferring it mostly because of the difficult situation we are all now. So finally, have the pleasure to be here in front of this audience to present some of our recent work you mentioned. So today I'd like to present our model, our work related to the inclusive breakup reactions. This is a work that has been done in the last 5 years or so in very close collaboration with my former PhD student, now postdoc, Jill Lei from China. So, well, this is more or less the outline of the presentation. So I know that the interest, according to the invitation, was mostly on the application to fusion of this. But before that, I think I should introduce the model itself, the model that we use for that. That is called the Ichimura-Austen-Vincent model. And for those who are not familiar with inclusive reactions. And then finally, we'll present the application to fusion of this model. And finally, some words on incomplete fusion, which I know is a very hot topic, and there are many people interested in that. So this is just a kind of historical motivation. This is the reason why we got interested in this particular problem. So many years ago, we were studying scattering of weakly bound of helium nuclei around Coulomb barriers. This is, for example, the case of helium-6 on lead. And this led to several very interesting theoretical developments. For example, this led to the development of the four-body CDCC method, which is, as you all know, an extension of the standard CDCC method that we use with Fresco, for example, to study the breakup of a two-body system. So we were very proud regarding these results, both because of the data. So our colleagues from Sevilla, Huelva, Madrid, they got very nice elastic scattering data for helium-6. These are actually the outcome of 2 experiments covering different angular regimes. This is an energy slightly around above the Coulomb barrier. And you see here the 4-body CDC calculation, which was done by one of our colleagues in Sevilla. So we were very happy with this result after a lot of effort from experiment and theory. But then when we looked at the alpha production channel, which as one might expect is a very dominant, a very important reaction channel, we had a situation like that. So this is plotted as a ratio between the alpha particles and helium-6, which is a kind of ratio between transfer breakup and elastic scattering. So first of all, we see that there are many alpha particles, so the ratio becomes close to 1 at large angles. And then second, when we compare with the same calculation that we used for elastic scattering, the one that reproduces elastic scattering, we found that this calculation was underestimated by a huge factor, the alpha particle production. So these two results seem to be incompatible, because one would expect that if we cannot reproduce this, we hardly can reproduce the elastic scattering. So this puzzled us for some time. And this is, as I said, the reason why we started thinking on this problem of inclusive reaction. This is an example of inclusive process, because in this reaction, only alpha particles were measured, only charged fragments were measured. But the neutrons, for example, which are dissociated from helium-6, are not observed. So putting the problem in a more general context, so that and considering a situation which is a bit simpler than helium-6, so thinking on lithium-6, because for lithium-6, to some extent, we can use a two-body picture, a two-body model. So for lithium-6, we can think of a similar situation as we had before, and just try to think what are the possible contributing channels to the, for example, alpha singles cross-section. So if we measure alpha particles, what is the source of these alpha particles? Well, first of all, we have the natural channel that we would include in fresco calculation for examples, that is the elastic breakup channels. That is called at higher energies. This is called diffraction, or some groups call this a non-capture breakup. This is just the dissociation of lithium-6 into deuteron and alpha, leaving the target in the ground state. And then we can also have this non-capture breakup, but with the target being excited. And we call this inelastic breakup. We can also have situations, if we only detect alpha particles coming out, we have the possibility that the deuteron is absorbed in some way by the target, or is transferred to the target, or partially transferred to the target. We don't know, because we do not observe that. So we might have alpha production when the deuteron interacts non-elastically. We could call this transfer or incomplete fusion, depending on the context. We could have another breakup mode. If we observe the deuterons, we have the opposite process, in which the alpha somehow interacts non-elastically with the target, and deuteron survives. So these are the channels, the collection of all these three channels here, this plus this plus this, we call these non-elastic breakup channels. And then finally, if we are observing alphas or deuterons, we might have the possibility of forming a compound nucleus and then evaporating particles. So these particles arise from a different mechanism. This is not a direct process. This is a compound nucleus process followed maybe by some evaporation of particles. And this is another source of alpha particles and deuterons, and for a general case. So for a reaction of a two-body projectile like this one, composed, that we denote by A, composed by B plus X, in which we observed only the singles, only one of the fragments, for example, B, and then we do not observe the rest. So we can say, according to this picture, that the yield of B particles will be the sum of the elastic breakup, the diffraction part, plus non-elastic breakup contributions. And clearly this non-elastic breakup is something difficult, because it includes many possibilities. And then finally, we might even have some contribution from compound nucleus, as I said. We have, what about the theory? When we try to compare with experimental data, for elastic breakup, as I mentioned before, we have an assortment of tools and methods. We can calculate elastic breakup accurately using CDCC or DWBA, for example, even with FADEIF. Some groups have made very impressive developments on FADEIF. So we have many tools to compute this component of the cross-section very accurately. Also, if we are considering these contributions here, this complete fusion, then we could rely on these statistical models and so on, followed by evaporation model like phase 2 codes, this kind of tools. But what about those contributions here? So first of all, we might try to include all these contributions to non-elastic breakup channels, that's including by, let's say, by brute force, including one by one all the channels that might contribute. And using our standard tools at hand, such as DWBA, or we could even use CRC, cathode reaction channels calculation. So these methods, as you all know, are included in standard codes like Fresco. However, so this procedure, even in specific cases, we may reproduce data, has some limitations, has some restrictions. So first of all, the final states of the system, so we assume that we detect B particle and the X particle is the participant particle, the one that we do not observe. So the final states for the X plus A system may span in general a very wide range of excitation energies and angular momentum. So this means that in our calculation, our DWBA or CRC, we have to include lots of final states. So the model space, if we are to be realistic, will be huge. Then another difficulty is that if we just observe P particles, then part of the contribution of X plus A will be in the continuum. So we need to include the states in the continuum by making maybe some discretization, but still this is something that complicates further the analysis. And also, if we look at the residual nucleus X plus A, we do DWBA or CRC, we need to know the spectroscopic factors for those states. We need to know the spin and parity assignment. And this information in general is not known, it's not available, except maybe for a few states, low-lying states. When we look at any nucleus, a few MeV of excitation energy, we go to the databases, and well, first of all, we have a very high density of levels, and most of them will not even have some clear assignment. So this is another difficulty we have to face with this, say, brute force method. And then some of the final states. So by using DWBA or CRC, we typically think on direct processes, but we might have also non-direct processes. For example, the incomplete fusion part. So part of the cross-section in which X interacts with the target will consist in X being absorbed, fusing with the target. So this is an incomplete fusion or partial fusion process, which are not included by standard codes. So we have all these limitations. And as I say, even if we in practice can somehow overcome many of these difficulties and get a reasonable account of the data from the theoretical point of view, from the interpretation, this is not the ideal situation. So as an alternative to this approach, we could think on a way of computing all these non-elastic breakup channels using what I will call these inclusive breakup models, that I will present in a minute. And these inclusive breakup models are based in closed form formulas that provide an efficient and I may say also an elegant alternative. And the basis of these models is the fact that all these non-elastic processes, so non-elastic breakup, is due to the non-elastic interaction of X with A. All these non-elastic processes must be somehow encoded and be included in the optical potential describing X plus A scattering. So in particular, the imaginary part of this potential should account for all these processes. So we have to go back to the 80s to find the theoretical, the first realistic, let's say, approach to these inclusive breakup processes. And we find the works, for example, of Bauer, Gerard Bauer, in the 1980. Then Hussein Mahloud had proposed a very interesting paper that which they obtained one of the first closed form formulas for that. And then there were two more groups, one by Ichimura, Austen, and Vincent, that proposed what is called a pulse-form DWBA formula for inclusive breakup. And then there was an alternative, a similar formula, but in braille form, that was proposed by Utagawa and Tamura. Well, these models, they are not equivalent, and actually they do not even predict the single sections. There is a very interesting story about the discussions between these groups for many, many years, trying to convince each other about the limitations of the methods proposed by the other, limitations or errors or mistakes. And well, at the end, there was no clear consensus about which method was the best for that. But anyway, very recently, one of the problems at that time was that computationally it was not feasible to make a full implementation of those methods. So there were very few calculations, mostly by only this group, Utagawa and Tamura, but Ichimura, Austen, and Vincent, they did not even publish a single calculation using their method. So just they based their arguments just in theoretical grounds. So, well, for many years, these models, and I say, have been forgotten. And recently, I mean, like 5 or 6 years ago, several groups, including our group in Sevilla, thanks to the visit of Jean Lay for his PhD, his enrollment of Jean Lay, and also Brett Carlson from Sao Paulo, and Gregory Potel, Filomena Nunes, Ian Thompson in United States. So independently and with different motivations, we end up studying those old theories, implementing those theories. And there was even a workshop in 2016 devoted to these theories. So this is a picture that I like very much. It's Brett Carlson here representing this group, Gregory Potel here. Well, that's me. And he's Mahir Hussein. Mahir Hussein, unfortunately, he died last year. Mahir Hussein was, at that time, he was the only active person from all this that I mentioned. Well, I must say Gerard Bauer also is somehow active and not working in this particular field, but Mahir Hussein was active, and he got like a new interest in the subject. So it was very nice to have this workshop with the enlightening discussions with Mahir Hussein. And the outcome of this workshop can be found in this publication. It's a kind of white paper summarizing the discussions that we had in this workshop at MSU. Well, this is, let me present very briefly the Ichimura, Austen, Vincent model, which is the one in which I will base the results that I will present. I told you that there was a long-standing discussion between different groups. I will start from the end. So the end of the story is that we implemented all these different models, and we compared against experimental data. Well, on the basis of the agreement or disagreement with the data, we came to the conclusion that the model proposed by Ichimura, Austen, and Vincent was the most reliable one, and that's the one that we have been using for further analysis. So there is the original derivation of their model can be found in this reference from 1985, but I will present here not the derivation, which is very formal and well, requires some time. So I will present just a sketch, which is what I could say I would call a heuristic derivation of this formula. So we are dealing with an inclusive reaction that I write again in this form. So we have two-body projector, and this is a sketch of the process. B plus X, and we detect B. So B is a kind of spectator particle here, and X is the participant particle, is the one that we will not observe in a single spectrum. So X may interact in any possible way with the target. So this represents any possible process in which X interacts with the target. So the best single cross-section, neglecting here the compound nucleus part, can be written as the sum of two contributions. One contribution that corresponds to the elastic breakup, the diffraction part, the one that we can accurately compute with CDCC or DWBA, and then an additional part that is the non-elastic breakup that contains these other processes. The key part of this model is that the non-elastic breakup can be interpreted as the absorption that takes place in the X plus A channel. So this is essentially what we can compute with the optical model when we have a two-body problem. So we can compute the reaction cross-section of the absorption using the absorption of the two-body system computed as expectation value of the distorted wave, describing the relative motion between them. Here is a bit more difficult because we do not have a two-body problem, we have a three-body problem, but still we can, after some derivation, we can obtain a similar expression. So this can be understood as a generalization of the optical theorem to three-body problem. So we have the expectation value of this WXA. This WXA is nothing but the imaginary part of the optical potential describing scattering of X plus A. And this expectation value is computed with a particular function that is called the X channel wave function. This is a three-body wave function, this one here. And this depends on this coordinate X and A, but depends parametrically also on the momentum of the spectator. So this is a formula that depends on the angle and on the energy of the spectator particle. So we make an experiment, we detect the P particle at a given angle with a given energy. So this expression gives us what is the probability of producing these P particles by means of any possible non-elastic breakup. So you see here, this is a very compact expression. So we don't have to worry about specific channels which are populated, about spectroscopic factors, level densities, all these complications that we would have to incorporate in our calculation are encoded in the imaginary part of the optical potential, because this is actually the meaning of the optical potential. And this rho is just simply a kinematical factor, it's a density of states. So this psi x, that is a complicated piece of this calculation, describes somehow the relative motion between X and A, but not in a two-body problem, but in the three-body context. And it's computed, must be computed for each final state of B, each final angle and energy of B, by solving this inhomogeneous equation. This inhomogeneous equation contains, again, the optical potential between X and A, and contains this term here, that is similar to the one that we would find in transfer calculations, for example. This is a post-form expression, so this is the post form of the transition operator that is written explicitly here in the post-form transition operator. This psi b is a distorted wave describing the motion of the spectator. So we also describe the motion of the spectator particle with an optical potential, and the psi three-body is a three-body, the exact solution of the problem in a three-body approach that we can approximate later on. Somehow we will have to make some approximation for that. So these two equations essentially summarize the Ichimura-Austen-Vincent model. So with this double differential cross-section, we can compare angular distributions and energy distributions, or even double differential cross-sections. So let me show you now some results, some comparison with data. This is the case of deuterium on niobium 93, which only the protons are detected. So first, one might be tempted to do a CDCC calculation. CDCC calculation for that. So we may assume that these protons are the result of the breakup of the deuterium into a proton and a neutron. And we can compute this with CDCC, and this is actually what we did here. So the result of this CDCC calculation is this dashed line. So this dashed line, you see, is an order of magnitude smaller than the experimental data. So the single cross-section for protons are not originated by elastic breakup mechanism, something more complicated. So then we have to introduce the non-elastic breakup contributions, which in this particular case will correspond to the interaction of the neutron with the target in any possible way. But instead of including all these channels one by one, we use a formula from the previous slide. So we need just the optical potential between the neutron and the target, and then we have to solve many times these equations, because for each angle of the proton, we have to solve this equation. And the result of this is this blue line. I have to say, in this particular calculation, this three-body wave function that appears here has been approximated by, sorry, I think I went to the end. Yes. So in this particular case, this three-body wave function has been approximated by a DWBA expression, that is a distorted wave for the deuteron times the ground state wave function for the deuteron. So the calculations from this reference and the data from this one. Another example that this is one that we also found very interesting. That is lithium-6 on bismuth. Remember that we started with this problem with helium-6, but helium-6 is very complicated to start with, because helium-6 is intrinsically a three-body system. So we had to decide to go to a simpler system that shares some property with helium-6, but we can treat to some extent as a two-body system, that is lithium-6. So for lithium-6, that's by looking at experimental data, and this data are taken from Santra et al., shows a large amount of alpha particles. That's very similar to the situation with helium-6. And if the main mechanism producing these alpha particles were the elastic breakup, we would expect to find the same amount of deuterons. But this is not the case. Just by looking at the spectrum, you see that you have a much larger amount of alpha particles as compared to deuterons, which are located here in this region. So clearly, the mechanism producing these alpha particles, the dominant mechanism, is not elastic breakup. Still, if we can convince ourselves by performing CVCC calculations. So we start performing these CVCC calculations based on an alpha plus deuteron model of lithium-6. We include excitations of lithium-6 into alpha plus deuteron continuum. And the result of that is this magenta dashed line. The nice thing of this data is that they have a nice angular distribution from energies below the barrier to well above the barrier. So you can see the different evolution of the angular distribution according to the incident energy. But you see that neither below or above the barrier, we can't reproduce the data. So clearly we are missing the non-elastic breakup. So again, we apply the Chimura-Austin-Vincent model within the DWBA approximation, which means again this factorization. And the result is here. So we have now an additional contribution that is the green line everywhere. You see that green line by itself describes the experimental data. Then we have to add the two contributions incoherently. And when we add the two contributions, we get something that is not perfect with the data. It's a very reasonable reproduction of the data. Also, more recently, we have been applying this to scattering of halonuclei, like the popular beryllium-11 system. So this is, for example, beryllium-10 production after beryllium-11 breakup. And these are energy distributions. Remember that we can compute both angular and energy distributions. So here, this is the energy distribution for a specific scattering angles of beryllium-10. So what you see here is that for the small scattering angles, we can understand the data perfectly with the elastic breakup mechanism, with the diffraction mechanism that in this case was computed with an extended version of CVCC that includes beryllium-10 deformation. It is not relevant for the discussion. And non-elastic breakup is negligible. It's the green line here. But as we go to larger scattering angles, we can interpret at closer trajectories. Eventually, the neutron will start interacting non-elastically with the target, so we have some source of additional breakup. And you see that a bump here corresponding to non-elastic breakup develops and becomes larger as the angle increases. So actually, to explain the data, we have to include both contributions again. Now I will move to the, so this first part has been to show you the properties of the features of this Ichimura and Vincent model. And this second part is devoted to the application to fusion. So probably many of you are aware or familiar with this problem of complete and incomplete fusion, but this is just one slide to remind you the situation. So complete fusion is defined as a process in which the whole projectile is absorbed by a target, forming a compound nucleus. And there is an observation made by several groups, but I'm showing here the results from the group of Canberra, Nanda Dasgupta and her collaborators, showing the complete fusion of two systems forming the same compound. And what they find is that when the projectile is weakly bound, even if they end up in the same compound nucleus, the complete fusion is suppressed by a large factor. So this is found for lithium-7, but also for other weakly bound projectiles like lithium-6, lithium-8, beryllium-9. In all these cases, the reduction is very significant. It goes from 20-something per day, even 30%. And this reduction that is measured with respect to the barrier penetration model, or even sometimes with respect to couple channels calculation, including, for example, collective excitations, means that we do not understand what is going on because experimental results are smaller than the predictions by these calculations. So there has been many attempts and many works trying to interpret the situation. It was more or less assumed in the literature that this suppression is due to the competition with some other channels that subtract or reduce the probability of complete fusion. These mechanisms are possibly breakup of the projectile, the projectile breaks, and then incomplete fusion. And actually, incomplete fusion is interpreted in these some works as a kind of consequence of breakup, because incomplete fusion is modeled as a two-step process in which the weakly bound system, because it is weakly bound, it will break easily to two or more fragments, and then only one of the two fragments, only one of the fragments will be captured by the target. So this leads to incomplete fusion, and conversely, this will reduce the amount of complete fusion. So this kind of competition between incomplete fusion. However, having many calculations, mostly based on, for example, on semi-classical approximations and other. Here I mentioned one of these references that use a classical dynamical model in which they try to incorporate these mechanisms in the simulations. And what they find is that this process of breaking the system and then absorbing one fragment can only explain a small fraction of this, cannot explain this 30%, only a few percent. So there must be something that is missing in this interpretation. So the way in which we approach it, this problem is the following. So complete fusion is somehow linked to the other channels. All channels, direct and not direct channels, are related by the reaction cross-section. So this imposes a constraint to the amount of different contributions. So the reaction cross-section for in general will contain many contributions, but for the cases that we are considering here, like lithium-6 or lithium-7, that we can to some extent describe as a two-body system. So we can approximate the reaction cross-section as the sum of the complete fusion. Then some inelastic excitations of projectile and target, for example, collective excitations. Then we have the elastic breakup part, then the diffraction, dissociation. And then we have different sources of non-elastic breakup. Here we have two contributions because in one case we detect P particles and X scatters non-elastically by the target, and this is the opposite. So X scatters elastically, and then the other fragment B interacts non-elastically with the target. So this is approximated because we might have some other contributions, but this is the main assumption of the model. And now the thing is that reaction cross-section can be computed very accurately. If we have, for example, elastic data, we can compute this. And then for the other mechanisms, we have also tools that can be used to compute all of things. So this means that we can extract the complete fusion cross-section by subtracting to the reaction cross-section, we can subtract the different contributions. So for inelastic scattering, we can use couple channels calculation, for example. For elastic breakup, we can use CDCC. And for non-elastic breakup, we have this Ichimura-Austen-Vincent model. Might say that incomplete fusion is also included here. So the competition with incomplete fusion is taken into account because incomplete fusion is part of the non-elastic breakup component. So here we are also taking into account that complete fusion is partially reduced because of incomplete fusion. And this contribution is included here in the non-elastic breakup part. So let me show you, before showing the result of this, let me show you the contribution of these different breakup modes compared with the reaction cross-section. So we have the reaction cross-section that here is computed with CDCC, but in these cases that we have elastic scattering data, we have also the possibility of doing an optical model fit and compute the reaction cross-section, and they agree very well with each other, actually. So we start with the reaction cross-section, and we consider the other mechanisms. Here, I'm not including inelastic processes because in the cases that we studied here, lithium-6 and lithium-7 on bismuth, these inelastic contributions were very small. And actually for lithium-7, it has a bound excited state, is included in CDCC, so it's part of we include here as elastic breakup. So what we see here is that elastic breakup, that is triangles here and here, is a very small fraction of the reaction cross-section. So this picture in which the projectile breaks and then one of the two fragments is absorbed is difficult to support with this result because elastic breakup, this first step, is very small. The dissociation of lithium-6 or lithium-7 into two fragments, elastic dissociation, is very small. So it can hardly contribute or can hardly be a strong source of incomplete fusion. And then, on the other hand, the dominant channels contributing to the reaction channel are the non-elastic breakup channels. So in particular, this blue line here and here, this blue line corresponds to the alpha production that we have seen before, the experiment by Santra and the comparison with the theory. This alpha production channel is in all these reactions is the dominant channel. So we have here in the calculations that we can confirm this with the data themselves. Okay, so from this picture, what we may anticipate, going back to this formula, that the main competitor to the complete fusion, so the main responsible for reducing complete fusion is not the dissociation, elastic dissociation of the projectile, but this non-elastic breakup contribution that include this incomplete fusion. So this can be confirmed by comparing with the data. So we start, so these are the data from the Canberra group by the Nanda Dasgupta. And in magenta line, you have the barrier penetration model calculation. This is a calculation that does not take into account the internal structure of the projectile or target. So this is a single channel penetration model. And then this is our estimate for the complete fusion that is computed from the reaction cross-section by subtracting the elastic breakup and non-elastic breakup cross-sections. So this gives this red line here and here. And as you see, it can explain very well the complete fusion for the whole range of energies. We are considering only energies above the barrier. This orange arrow marks the position of the barrier. So we are considering only energies above the barrier in this study. And another conclusion from this study is that the elastic breakup mechanism plays only a minor role. So this somehow explains that calculations that try to use elastic breakup as the competitor of complete fusion, these calculations fail to explain the complete fusion because elastic breakup, as I've shown here, is only a small contributor to the reaction cross-section. It's also interesting to see how the situation changes with the separation energy, because so what is the role of the binding energy of the process? So for that, I consider a specific incident energy for lithium-6. This is 33.6 MeV, slightly above the Coulomb barrier. This position here, this is the separation energy, and the red arrow indicates the physical position. So we can go to more weakly bound lithium-6 or more bound lithium-6. So this is, of course, a theoretical study. And we can see the contribution of the different channels with the binding energy. And then we can see what is the extracted complete fusion. So what we see, the experimental situation is here. This a yellow circle is the experimental complete fusion. And then if we go to lithium-6, which is more bound, what we find is that elastic breakup, that is this black triangle, drops very quickly. Actually, it becomes completely negligible for energies of a few MeV. So clearly, elastic breakup does not contribute for system with a few MeV of separation energy. This is more or less what we expect. But what is interesting is that the alpha production channel remains important, remains significant, even for relatively high separation energies. And the other thing that we see here is that when we go to a strongly bound system, the complete fusion, the red line here, obtained by this method, obtained by subtracting elastic breakup and non-elastic breakup, converges to the prediction of the barrier penetration mode. So when we somehow force the system to be a compact one, it does not dissociate easily, then what we have is what we would expect in a situation without internal degrees of freedom, the barrier penetration mode. And then we go to the opposite direction. We go to the weakly bound system. So we decrease the separation energy. We go to a halo-like system. What we find is that the elastic breakup becomes an important competitor. So for halo systems, this elastic breakup, it is an important contributor to the reaction cross-section, and then can affect also the complete fusion cross-section, but apparently not for lithium-6 or lithium-7 and so on. So these are the main conclusions of this part of the work. Now, another question is this interpretation of incomplete fusion as a two-step mechanism. So what is the evidence for that, or is it supported by the calculation? Does incomplete fusion takes place as a two-step mechanism, where the first step is the dissociation of the projectile? So this is illustrated here. First step is a dissociation of lithium-6, and the second step is the absorption of one of the two fragments. This is the usual picture that is used for incomplete fusion. And this is schematically shown here. So we have this initial partition, A plus A. So the system breaks into the two fragments, and then one of the two fragments is absorbed by the target. This is the two-step picture, the breakup fusion picture. Now, we can have also an alternative interpretation that is a direct or one-step picture in which the fragment X is absorbed directly by the target. So this is not a two-step, this is a one-step picture. So how does incomplete fusion behaves? What is the mechanism? What is the interpretation? Well, to answer this question, we cannot rely on the DWBA form of the Ichimura-Austin-Vincent model, because we have to incorporate explicitly this dissociation to the continuum. And for that, we have to go to the original formula that is written here for this channel function. So in this homogeneous equation, we have to put here the three-body wave function that includes not only the ground state, like in DWBA, but includes also explicitly the unbound states. So for example, we may approximate this by a CDCC expansion in which we explicitly take into account the different states of the B plus X system. So schematically, the CDCC wave function will contain contribution from the bound states, one or more, and then contributions from the continuum states. So we have to apply this. We have first to solve the CDCC equations. From that, we will have the contribution or bound states and continuum state in this function. And then we plug this function into this term here, this source thing, and we solve this in homogeneous equation. And this has to be done many times because remember, this depends on the final state of the V particle. And so to the extent that we can separate this CDCC wave function into two terms, this means that the source term can also be split into two terms. One term that contains only the contribution from the projectile ground state. So this contribution, this rho bound that comes from this piece here, when we put it into here, describes this process, the process in which the fragment X is directly absorbed from the ground state. And then the second contribution is the one in which the fragments, they first dissociate, and then one of the fragments is absorbed. So by making calculations, neglecting one or the other contribution, we can compute the importance of these two effects. I must say that these two contributions do not add incoherently because they enter this source term. So the final result is not the sum of the two terms. There are interferences, but we can get an idea of the importance of these two terms by making different calculations. So these are the results, again, for lithium-6 on bismuth reaction at 36 MeV. And we compare here this CDCC version of the Ichimura-Austin-Vincent model with the original DWBA1. And this is the cross-section as a function of the final energy of the deuteron plus target system. So this is somehow excitation energy of the final residual system X here. So what we find, then we perform three calculations in which one, we used the full CDCC wave function, a second calculation in which we retained only the ground state wave function, and then finally a calculation in which we retained only the continuum contribution. So you see here that the most of the contribution comes directly from the ground state. So if we remove the continuum from the CDCC calculation, so we have this green line here, we essentially get the full result. So this line here that you barely can see is a contribution of this two-step process. So this result tell us that this incomplete fusion, on more generally this non-elastic breakup processes, is not a two-step process, as commonly assumed, but just a direct process going directly from the ground state. So this is the main conclusion of these calculations. So then the question is, what is then the mechanism that is behind this large incomplete fusion probability? Why is that probability that large? Why is this much larger than elastic breakup? Why is it so important? It does not even require to break the system. How is possible that the fragment X goes directly to the target being absorbed? Well, then to answer this question, we resort to new calculations. So here, what I try to explain what is shown here. So we again consider these two reactions, lithium-6 and lithium-7 on bismuth at energies around the barrier, and we compute two things. Well, one thing is the reaction cross-section for the free process in which the light fragment, the one that is absorbed, is interacts with the target. So with an optical potential. So this black line here is as a function of the deuteron target, of triton target, gives the reaction cross-section. We see that the reaction cross-section, as a function of the energy, drops very quickly and becomes negligible for energies below the barrier. So this is the barrier for the deuteron target or for the triton target, for the two-body system. But then, if we do the calculation for the three-body systems, for lithium-6 as a projectile, these are for different incident energies for lithium-6, 28, 34, 40 incident energies. So these two energies are above the barrier for lithium-6. So we see that the contribution for X, the light particle being absorbed, so the deuteron being absorbed, is very large, even for energies below the barrier of this light particle. So we have a large contribution for the deuteron being absorbed or the triton being absorbed, even for very small energies of this light fragment. So you see these tails here, or this tail here, are below the barrier for the deuteron target or triton target. So the conclusion then is that this absorption is enhanced in the three-body reaction with respect to the free two-body case. That is the black line here. The reason for that, we can interpret this using this idea of the Trojan horse mechanism. So the fact that the lithium-6 or lithium-7 is above the barrier makes that this lithium-6 is able to overcome its own barrier and is bringing inside the barrier the light particles. So here, for example, lithium-6 is bringing the deuteron inside its own barrier, like a Trojan horse. And then the deuteron, once it's inside the barrier, is easily absorbed by the target. So this is, of course, the same mechanism that is behind the Trojan horse method that is used in nuclear astrophysics, and that allows to measure the cross-sections, the two-body cross-sections, for relative energies here, for which the two-body reaction reach a very small cross-section. So by using a three-body reaction, a surrogate reaction, we can obtain a large cross-sections for very small relative energies for these two-body systems. So it's the same idea. So essentially, this is our interpretation for incomplete fusion. Complete fusion is very large, not because the system is weakly bound, that as we have seen before is not so relevant, but because of this Trojan horse mechanism that is allowing the light particles to be captured by the target. And the final slide here is just an idea of to split, to separate the incomplete fusion, to isolate the incomplete fusion from non-elastic breakups. Because all the time I've been saying that incomplete fusion is part of non-elastic breakup. But non-elastic breakup contains incomplete fusion, but contains other things. For example, non-elastic breakup contains the target excitation, for example, and this is not incomplete fusion, of course. So how do we separate? How do we split? How do we isolate the incomplete fusion from non-elastic breakup? Well, this is, in my opinion, this is a non-trivial problem. So a very naive idea would be just, again, resorting to this Ichimura-Austen-Vincent model to split the imaginary part that contains all these processes, to split this imaginary part into two contributions. One contribution that is the direct contribution, direct channels, like a target excitation, for example, and from another contribution that is the compound nucleus. So X fuses with A, and this contribution here can be associated with this incomplete fusion. So then we can compute incomplete fusion applying the same formula as before. So again, we apply the Ichimura-Austen-Vincent formula, but here we replace the total imaginary part by only the fusion part. So in principle, the theory that looks also sensible, but the problem here is how to make this separation. So this is a non-trivial separation. So when we have a general system, it's not obvious, in my opinion, to separate these two terms. Commonly, sometimes one tries to reproduce the fusion part by using a very short range potential, very deep potential, but then one has to make a choice for the depth of this potential. The parameters of results should be independent for that. And well, to me, it's not clear that this is a choice that will be valid in general, but could be accurate in some cases, but I'm not sure that this will be valid in general. There are some similar attempts of using computing complete fusion, but using similar but alternative approaches by several groups, and I highlight here the works by Vivek Parker, one of our hosts, and also by Brazilian groups at Rio de Janeiro that have published recently an interesting work on that. But I think I don't have more time for that, so I will just finish up by showing my conclusions. So I hope I have convinced you that these inclusive breakup processes that are very relevant and appear in many situations. I have to say, I have not mentioned all these situations, but they appear, for example, in the surrogate methods for astrophysics and Trojan horse that I have mentioned, in some other applications. And for that, we have these nice theories developed in the 80s, which has been revisited recently, and that provide an efficient and elegant way of computing this inclusive breakup cross-section, particularly the non-elastic breakup part that is the difficult part. We see also that using this, combining this theory, Ichimura-Austen-Vincent theory, with the calculation for the different contributions to the reaction cross-section, we can understand the complete fusion suppression for weakly bound projectiles. And then finally, there is this problem of incomplete fusion, which, in my opinion, there have been very important progresses in the last few years, but that we still don't fully understand. But I'm sure there will be interesting results in future by many groups which are working on that. So let me just finish by acknowledging my collaborator, Jill Lay, who has been responsible for essentially all the calculations that I have presented here, which are part of his PhD thesis, and we have kept collaborating after that. He's now at the University of Pisa, in Italy, working with Professor Angela Bonacorso. And also, I like to somehow to dedicate this seminar, this talk to the late Mahir Hussein for all the contributions he made to the physics in general, nuclear physics in general, in particular, to this nice problem of inclusive breakup, and also for the many stimulating discussions that we had the opportunity to have with him until very recently. So, well, thanks very much, and that's all from my side.
Thank you, Professor Moro, for a nice and informative talk. And congratulations for you also for these two back-to-back PRL publications. Now the talk is open for discussion. People can raise hand and then we'll call one by one. You have to raise hand. Okay, fine. There are several people. So I invite Dr. Aradhana Srivastava to give for a question.
Hello, thank you for a very nice talk and explaining such a complex formalism in a simpler way. So what I would like to understand is the process which you tried to explain, the Trojan horse, because it's a main question how this triton is getting or deuteron is getting captured. So it is not from the excited or unbound states of the 6 or 7 lithium, but you are saying they are just sucked. They are simply sucked from the ground state as they are approaching the target. And you cannot even classify it as a triton stripping like you do it in a normal transfer reactions, because you take care of various spectroscopic factor and all. I'm still like it is simply sucked from the ground state, and the projectile is not excited. I mean, can you please throw some more light on that?
Yeah. Sorry. Yes. So that's. So could you repeat the question? So I just missed the last piece.
The last piece was, can we consider it as a direct stripping, triton or neutron stripping from the ground state, as you treat them in a direct reaction theories? Because if you treat them like that, they won't give you large cross sections like what you get.
Yes, well, in reality, this is not, you can think of this, of course, as a stripping, but as I said, in part of these cross sections will correspond to the transfer of this fragment to bound states, and this, I think we all agree, is a transfer. So something that I did not mention is that in these formalins, we can include on an equal footing the contribution in which this unobserved particle, the light particle, goes to bound states or to unbound states. So in the case of bound states, this is not different from a transfer calculation, and this is in fact a transfer. The only thing is that more naturally, we will describe this with a dispersive optical potential for negative energy. The problem when we go to positive energies, then I think we enter in a kind of matter of terminology, because if the light fragment goes to an unbound state, probably some groups will call this transfer to unbound states, and maybe some other would call this incomplete fusion or absorption or partial fusion. So even experimentally, I don't know how easy it is to disentangle these two things, because we can think the light particle being somehow fused with the target in a continuous state and then evaporating. Or we may think of a direct process in which we just place this in some orbit in the continuum and then decays. So probably the difference there is very subtle, mainly in the time scale that this process is occurred, and probably experimentally is. I'm not experimentally, but I guess it's not trivial. It's not obvious how to disentangle. So, yes, I think it's fair to call this a transfer, a cluster transfer. If I may,
Hello.
one find is that actually the final result, that is this TC here, transfer to the continuum, this is just the contribution of transferring the neutron, in this particular case, to a set of final states that can go from negative to positive energy. And this tends to agree quite well, but the effort that is required to do this calculation is larger because of all these uncertainties. But well, just trying to summarize, I would say that we can also think of a cluster transfer. It's okay to call it a cluster transfer, but sometimes this terminology can be misleading because maybe the process, the physical process, is not a transfer in the usual sense, but involves the formation of some kind of compound, some partial fusion. So in these formalins, we cannot distinguish these two things because everything is encoded, is included in the imaginary part. And as I said, it's not trivial how to split the direct part that we will call that transfer to the continuum from the partial fusion part. This separation is not trivial experimentally or theoretically. So, well, we just called it absorption or non-elastic breakup processes. But I know that other people might call it a transfer or cluster transfer.
Okay, thank you.
Next is Dr. Santra.
Hello, I have a related question also regarding this transfers. If we believe that 6 lithium itself is going fast, overcoming the barrier, and there it is breaking up, suppose alpha and into as well as deuteron, then the deuteron capture is large. That is what is giving out the large enhancement in alpha going out. But why not the other way? Suppose because both of them have overcome the barrier. So alpha capture, why it is so less compared to deuteron capture? And
yes, well,
does your calculation explain both the experimental values, or just it is reproducing the alpha?
Well, that's you know, we contact you because we were interested in the deuteron as well. In principle, the model can be applied to both fragments. So you have to interchange the roles of participant and spectator. So we can consider that the participant, and this is what we did in this calculation, the spectator can be the deuteron and the alpha can be absorbed. First, well, the alpha absorption is smaller, that corresponds to the magenta line here. Well, essentially the reason is that the alpha reaction cross-section, the interaction of the non-elastic interaction of the alpha with the target is smaller. First, because of the charge, because the alpha has charge twice that of the deuteron of the triton, so the probability for the alpha being absorbed is smaller. And also there is a question.
But the alpha energy is also double. Alpha energy.
Yes, that's true. And this comes the second argument, because this argument is not totally true, because we have the counter example of beryllium-7. Beryllium-7 is very interesting because both fragments, helium-3 and alpha, have the same charge. So in that particular case, and the alpha production is still larger. So that comes the second argument. So the argument of this of the barrier, I agree with you, is not a very strong one. But then the second argument is that the reaction cross-section of the deuteron with the target, or triton with the target, is much larger than the one of the alpha. The alpha is very compact, and the deuteron, for example, can interact by a DP reaction, or for example, the triton can very easily capture a proton to become helium-4, so we have very positive Q value. So according to the calculation that we have done in different systems, the main reason is that the reaction cross-section of the light particle is larger than the one for the alpha. So alpha is a very compact one, so it's not easy for the alpha to produce non-elastic processes. This is included in the imaginary part of the potential. And here a problem that we have found with some cases in which the reproduction of the data was not so good is that we are missing realistic optical potentials. So for example, we need a realistic triton potential, and there are very few optical potential in the literature for specific energies, but for these calculations, since we cover a range, we span a range of final energies, what we need is an accurate optical potential for different energies going from negative to positive energies, and this is not available in many cases like Triton. So, well, I don't know if I answered your case. In this particular case, we found a strong dependence on the optical potential of your data that you kindly provide, and we didn't work further on that, but what we found, different potentials gave very different cross sections. So probably in some cases, the problem is to find those relative potentials. But in principle, the theory could be applied to both fragments. There's no limitation in principle for that.
Yeah, no, if the other fragment could not be reproduced, then how means how well is the theory? That's the question. Whether that means it is not valid for one of the fragments and it's valid for particular fragment, which is alpha. Is it right?
Well, but I wouldn't blame the theory and the reaction theory. In that case, I would probably think of a problem with the optical potential. In some cases, for example, in the beryllium side, we have been able to reproduce the production of both fragments, helium-3 or alpha, but again, with a strong sensitivity of the potential. So,
and what about other fragments? Suppose in 6 lithium on Bismuth case, and suppose 3 helium, triton, proton, they are also coming. So have you ever tried to explain them in addition to alpha?
Well, since here we rely on a two-body picture of lithium-6, and this picture is alpha plus deuterium. So these other channels, for example, these tritons are out of the model of our model here. So to explain the tritons, we should think on a different description of lithium-6, not as alpha plus deuterium. Or for example, I can think of a channel in which the deuteron captures a neutron from the target and produces tritons. So this is a possible mechanism, but this mechanism is again included in the non-elastic breakup. So we cannot compute these specific channels, because what we compute in that case are all the channels that contribute to the deuteron target absorption. One of the channels will be the DT channels producing triton. If we are interested in a specific channels, then we shouldn't use these theories, which are to avoid the calculation of specific channels. So in that case, I think it would be more useful just to do a specific calculation like DWA or CRC calculation for this particular channel, producing tritons or producing whatever channel one is interested, I think.
Okay, thank you.
Okay, now to Dr. Ramachandran.
So if you see this next slide, slide number 13, you have shown that at the lower energy, the direct breakup cross section is rapidly rising, which is insignificant at higher energies. Is there any kind of intuitive picture for this? Why this is rising at very low breakup threshold or separation energy? Is there any kind of reason for that to rise?
Yes, well, when we decrease the separation energy, the wave function extends further, so the probability of elastic breakup increases. This is more or less what one finds for halo nuclei, for example. We have a less bound system, and it's easier to excite to the continuous states. First, because we have the breakup threshold is smaller, so we need a small amount of excitation energy to reach the continuum. The other reason is that the system becomes more extended, the wave function. So it's easier to produce the breakup because the overlap with the target nucleus is larger. So somehow in this region here, we find the same kind of phenomena that we would find for halo nuclei. It's not the same because it's still a charge particles, so it's not like beryllium 11 and so on, but well, it's a kind of halo-like system in terms of separation energy. But essentially, is that when we have a very weakly bound system, it's very easy just to dissociate by just kicking it with a small amount of momentum or energy. So we don't need much energy. So that's essentially the reason, the physical reason for that rise. Yeah.
Okay, thank you.
Now, Dr. Sanat Pandit.
Hello.
Yeah.
Hello. My question is that you are using optical model potential for different capture of these different clusters, and how you means fixing it means for alpha and for deuteron they are different. I feel so in your model for 6 lithium for deuteron or alpha you are using different optical model potential. How are you fixing these potentials?
Well, yes, that's true. So we have here several optical potentials that we have to introduce. So, for example, if we use the DWBA version of the method, we need the lithium-6 potential. This potential is typically in our calculations is obtained from the elastic scattering data that was also available in this for this reaction. So this is for the lithium-6, and then for the alpha, for the fragments, for the cluster, the two clusters. Then we have the problem that I mentioned. So in these calculations, when we solve the equations for each final energy of the detected fragment, then we should have in principle different potential because the potentials are energy dependent and we are covering a range of energies. And also by energy conservation, this means that we have different range of energies for the undetected and observed fragment. So the deuteron, the triton, for example, these calculations. So again, we need an optical potential for that. So what we try to do in these calculations is to go to the literature for some global potentials. So sometimes, in some cases, for deuteron, for example, you have many global potentials that span a wide range of energies. For some other cases, well, even for alphas, we have global potential, but for some other cases, like triton, helium-3, there are very few global potentials, and they are not, when you try to push them outside the range of validity, they don't behave very well. So this, as I said before, is an important source of uncertainty in this calculation.
I just want to interrupt. Those potentials are for the incoming channel potential. Here, what the assumption is that your lithium already crossed the barrier. So now I feel it has to come out from the barrier, these different clusters. And in this case, I feel alpha supposed to be facing more barrier than the deuteron. Hello.
Yes, I'm not sure. So you mean for the final state?
Yes,
potential?
Because you are using. If you go to the last.
So for example, in this equation, you have here somehow the different role of the different potentials. So in the final situation, you have the V particle, for example, the alpha particle that is coming out with some energy, and that's the energy in which it is detected in the experiment. So this means, so this alpha particle is described by this distorted wave. So we need to evaluate this distorted wave at the appropriate energy for the outgoing particle. I don't know if this was more or less your question. And then for the incoming channel, so we have here, for example, the three-body wave function. If we approximate this, for example, by a CDC wave function, then we have to use the appropriate potentials for the incident energies for the alpha target and the deuteron target, for example, to compute this three-body wave function. So try to use the appropriate potential in each part of the equation. But I'm not sure that that was your question. Maybe I didn't get it right. Sorry.
No, my question is that your optical potential you're using when 6 lithium is entering in the barrier at that time, the optical potential between target and the 6 lithium, it is that elastic delta fit optical potential parameter. But when you want to use in the exit channel, at that time you have to use this absorption potential, deuteron plus target or alpha plus target. And this potential may not be correct if you consider the incoming channel global potential, which is also obtained from the fitting of the elastic data.
Well, yes, that's why we use different potentials for the outgoing particles. So as I said, for the outgoing alpha, well, we have to use a potential for the final energy of the alpha that is different from the energy of the alpha in the incident lithium-6. Then, well, the lithium-6, in principle, the potential when it is approaching, if it is a perfect optical potential, it should describe the lithium-6 coming in for the different distances. Which is probably not the case, because here comes another difficulty, that optical potentials are obtained typically from elastic scattering. This means that an elastic scattering is only sensitive to the tail of the potential. And now if we want to compute the wave function when the systems get closer, then we need the potentials for the inner region. And we don't know how this potential is. We don't have a clue of how we should modify this potential. We don't know how the potential is in the interior, because we have many effects, like Pauli blocking and many things that can be density dependent. There are many uncertainties of these potentials when the systems are very close together. So this could be also interpreted as a kind of source of uncertainty of this model. So I agree with you that this is a problem, just to describe accurately the lithium-6 potential for the initial state at the different distances. But well, the best I think we can do right now is try to evaluate each potential at the appropriate energy. So we have a lithium-6 optical potential at the incident energy, and then we have the alpha potential for the alphas coming out that is evaluated for each final energy. So we have to change the potential for each final energy in principle, if we have this potential. And also we have the potential, this U potential that describes the light fragment with the target, the participant with the target. And again, this potential is energy dependent. So we have to to introduce here an energy dependence, and to replace this potential for each final energy of this fragment with the target, we have to change this potential. But, well, with all these limitations, we try to do our best in the calculations, but we are aware that sometimes we might have significant uncertainties due to this choice.
Okay, thank you.
Okay, Dr. Mahata.
Hello.
Yes.
Yeah. So actually, my question or comment is related to Dr. Satra's query that if the Torion-Horst picture is correct, then both alpha and tritron or deuteron should be captured equally. But you see, it is the alpha, like alpha production cross section is very large compared to the deuteron or tritron. Mm-hmm. That may be related to the Q value, and that actually kind of the phase space will be more for alpha, means that the K alpha will be range will be much larger or something. That's why maybe it is giving larger alpha cross section. So can you comment on that?
Yeah, well, we think that the main reason is that the the reaction cross section for deuteron or for tritons is larger than the reaction cross section for alphas when they are evaluated at similar energy per nucleon. So I think that's the main reason. So yeah.
No, but you like this picture, so no, that that picture is two-body reaction picture is not correct, no, because you are seeing lot of cross section even below the barrier. Yeah, so
this is
I feel that the Q value. Yeah, the Q value has, I think, a strong influence. Yeah, because that controls the range of momentum, no, on your third party.
So I think essentially it's sorry.
No,
so I
continue.
think the reason is that for deuteron, for example, we can imagine the TP channel, and this is part of non-elastic breakup. We have a DT channel, so there are many channels that can contribute because they have favored Q values and so on. But for alpha particles, we don't have those strong channels. So I think that's the main reason, that for the deuteron or triton, there are many strong channels that can contribute because of Q value or whatever reason, or spectroscopic factor or whatever. But for alpha particles don't like releasing particles or getting particles. So it's not favored stripping or pickup of anything. So for alpha particles, essentially we can excite the target, probably it's a small contribution here, or we can fuse the alpha particles. So we can have kind of incomplete fusion of the alpha and nothing else. But for the other particles, we have some direct channels that are probably very, very important. So that's our interpretation. Don't know if it is correct or not, but that's our interpretation.
No, I just wanted to know the wave function of the outgoing particle, no? How much it is different for the alpha and tritron, or whether that makes the difference.
You mean which wave function? Sorry?
The outgoing particle in case of alpha escape is alpha, and other case is the tritron, no?
Mm-hmm. Yes, you mean when it acts the wave function as a spectator, the one that we do not observe?
Yeah.
That well, in that case, this function is described with an optical potential, and this again it has an effect, because in the case of the alpha particle, it has less absorption, for example. So we have a more probability of survival of the alpha particles than, for example, for deuterons or tritons. So again, this is included somehow in the optical potential, the survival probability of one of the fragments. So here we have like two things. We have the survival probability of the spectator particle, and then the absorption probability. So this is the picture actually that is used in aconal calculations at high energy. So we have the product of two things. So the two effects, I think, are important. When we observe the alpha, we have something that survives very easily. And then the particle that interacts, the deuteron, the triton, interacts very strongly because there are many channels that can. And in the other situation, the survival probability of a deuteron of a triton is smaller because there are many processes that can absorb these particles. So what I mean is that it is more unlikely that the deuteron or the triton survive as such, and it's likely that there are processes in which this deuteron or this triton interact non-elastically with the target, and may pick some neutrons or perhaps any other process.
Okay, thank you.
Somehow, something that I like to say here is that these calculations are involved. So sometimes the interpretation is not so easy. So many times we face a situation in which this common saying that the computer seems to understand the problem, but we don't fully understand the problem. So, so sometimes we are in this process of getting some results. Sometimes even the results reproduce nicely the data, but it's not easy to find a simple interpretation of what's going on. So something that we still have to clearly to work harder, and is to try to not just to compare with data and say this is good, but trying to find interpretation of what we have found. And as I said, these are non-trivial calculations. It involves a lot of computational parts, but I think that it's by combining different calculations, as we try to do here, for example, I think we should be able to learn about the processes that are behind this and try to understand these differences between the alpha absorption, theta absorption, all these things. But I might say that it's not always trivial for us to get interpretation of the results.
Does Q value go inside into your calculation somewhere? I also agree with Kripa regarding this Q value, because in one case it is positive, another case is negative. So does Q value go into your calculation anywhere?
You mean the Q value? Well,
of
Q value for
D plus target or alpha plus target in that case?
Well, this goes
because their Q values are in opposite directions. So that really
yes,
play a
but
role.
this should be included in the optical potential.
Yes,
so
if you include and see, I think it will.
So we have a very strong channel with because of the Q value, for example.
Yes.
So this means that this is included here. So or here. So in the imaginary part, yeah, it should be there. So we don't include, the point here is that we don't include one by one, because if we were including all these processes, capture of one neutron, one DT, DP, then we will not be discussing about Ichimura-Austen-Vincent model. We would be discussing about coupled reaction channels calculations or doing first law calculations with 200 states and so on. So this is a different way of approaching the problem. If we are interested in looking on a particular channel and try to understand why this particular channel is important and not the other, then this is probably not the tool for that, because here what we try is to, we don't want to separate the different processes. We just have an experiment and they measured B, and we just want to compute the total yield for this B, and we are not interested in the specific contributions to the imaginary part. And now the questions that you are posing are, what I want to know, what is the importance of this DT, what is the effect of the Q value? All these should be contained here. So that's the point. One could confirm this by doing CRC calculations in some cases, but this is a different way of looking at the problem, I guess. I think.
Okay.
So the answer to your question is, well, the Q value on any effect enhancing some particular channel should be included here, assuming that this optical potential is perfect. But of course, in practice, we rely on approximate optical potentials and global phenomenological potentials and so on.
Okay. Thank you.
Anybody else? I don't see any raised hands. Okay. Can I ask one question?
Of course.
Okay. How do we understand the universal behavior in alpha production for, let's say, lithium-6 or lithium-7? What is your opinion?
Well, I think you have a long report on that, right? So probably you are in a better.
No, we have left it unanswered. We are not. We have just given the picture, but we have not answered that question.
Mm-hmm. Yes. Probably I think the point is that this here, when we talk about inclusive breakup processes, we are not selecting a specific process in particular. So when we look at a specific process, then we may find very different situations depending on which system we study or do a transfer reaction to a specific final state. The result of this will depend on the spectroscopic factor of this particular final state, on the spin, the Q value, and so all the details. But when we add up all these contributions, we have more like a geometrical situation. So we have something that is more or less insensitive to some extent, is insensitive to the details, specific details of the final states. So we are summing like all the single particle strength if we want, and then probably the outcome of this result gives us a sort of a bulk cross-section that depends mostly on probably on incident energy per nucleon or something like that. So we get something that approaches more like a geometrical cross-section or something similar to what we have in the server limit when we go to high energies. But so I have the impression that it goes more or less along this direction. The fact that we are adding up all processes and we have a kind of bulk absorption that is not dependent on specific details of the, for example, of the target nucleus. It does not matter much. It is, we use one nucleus of another. If we are doing stripping or pickup, then it's very important what is the target, what is the projectile, what are spectroscopic factors, all the details for this specific transition. But here, it's true that if we change one target by another, it doesn't matter much, because at the end we will be adding many processes and we will have fusion, we will have a lot of things that are common more or less related to the bulk absorption of this target, and they are not related to some specific process or some specific transition. This is my naive interpretation. don't know if it makes sense to you, but this is the idea that I have.
Okay, yeah, fine. Another question is regarding the, do you have any plan to take these calculations for beryllium-9 also?
Beryllium-9, it's very interesting, of course. We have thought about that, but it has a problem. It's a three-body system. So beryllium-9, it's 2 alphas and 1 neutron. So ideally, in that case, we should start with a three-body model. That's also the reason why we have been somehow avoiding the helium-6 case, which was the one that motivated us to enter into this business. But in that case, we should have here probably something like B plus X1, X2, and then consider different situations that probably experimentally can be distinguished, like the neutron interacting with the target, and then the 2 alphas coming out and then decaying because beryllium-8 is not bound, or one of the 2 alphas interacting with the target, and then we have helium-5 star, let's say, and again we have alpha particles. So for sure we will have lots of alphas coming from many different processes, but to properly tackle this, I think we should probably go to a three-body model. It was an attempt a few years ago by Mahir Hussain, who published some extension of this because he was really very excited with this revival of these theories. So one of the last things he did was to develop a theory, a very complicated one, I must say. So you go to the paper, in which he started with a three-body description of the projector and consider all these different contributions. This is a problem that I find very appealing because there are many situations like that, beryllium-9, or even for systems like lithium-6, it could be better to have a three-body model like alpha, proton, and neutron, boron-8, for example, alpha, helium-3, proton. So this would allow to study more diverse processes. As I said before, there are some channels that we cannot study because we are somehow restricted so far to two-body models. But if we released this restriction, we go to three-body description of the projector, and that would allow us to think of some other process. Lithium-8 is another example of that. So, well, I don't know if it is interesting for experimentalists, which I think it is, I think that would be also important for theorists to have this motivation from the experimental side, to know that there is an interest in having these predictions, which I believe there is an interest. I think that it's worth probably thinking on that problem.
Okay, thank you. I think Dr. Aradhana Srivastava was okay, yeah.
Just one small clarification. Your this elastic breakup section, for example, if it is for 6 lithium, and you don't capture both alpha and neutron, you both escape. So do you consider only states near the breakup threshold, or you take a state, you take some up to very high excitation energy of when both of the fragments are not captured? Do you take states only around the breakup threshold or even higher excited states?
Well, in principle, for any CDCC calculation, because we are talking about elastic breakup, so for elastic breakup, we do CDCC calculations typically, so we have to make sure that calculations are converged with respect to excitation energy. So depending on the system, particularly if we go to, I'm thinking even for deuterons, deuteron breakup in proton and neutron, we go to 100 incident energy. This means that we have to include excitation energies of tens of MeV to get converged results. So we don't restrict ourselves to the breakup threshold or to close to the threshold. We go to very high excitation energies until we get some stable converged results. But it depends very much on the case, on the situation, on the incident energy, for example, and so on. But in practice, yes,
okay.
For the deuterons, I remember we had to include very high excitation energies. Several things of MeV, I recall correctly.
Okay. Thank you.
Okay, thank you. Thank you, Professor Moro, for a very nice talk. Now I hand over to Professor Palip for the final words.
Thank you very much for all of you for attending the presentation.
Thank you, Professor Moro, for a very nice talk. And I should also thank Vivek for organizing this talk. Thanks. Thank you all.
Of course.
Thank you. Okay. Yeah.